So here's a fairly complicated question involving a compound pendulum. I know I talked about the previous question being really complicated, but this one is actually, I'd say, definitely up there with difficulty. So a uniform rod of mass m and length 2l has a point mass m attached to its midpoint. It's free to rotate about a horizontal axis perpendicular to its length through a point p x meters away, through a point x meters away from the midpoint. The rod performs small oscillations about the axis of the periodic time t. So firstly, show that t is 2 pi squared over 3g times l squared plus 6x squared over x, and find a value for x such that the periodic time is minimized. So, go ahead and try this problem, and when you're ready, come back for the solution. I'm just going to make sure that I have 2 pages for this. Yep, and there's a little hint for what's coming. Okay, so again, I essentially copying this diagram off a separate screen, but we have this rod, center of gravity here, and it's going to be some mass x, or it's going to be a distance x away, so I'll just call the mass y for now. Call that y, distance x, and this is of length l, so each of these are length l, as this is the center of gravity. So, moment of inertia about c is simply just a third ml squared, and about y, following from the parallel axis there, I have to think about that for a second, is ic plus m times the distance away from it squared. So we have 1/3 ml plus mx squared, which is also the moment of inertia of the point mass, funnily enough. So therefore, the moment of inertia of the system is 1/3 ml squared, that's the about c. Then we have the mx squared twice. Yeah, so yeah, we have the mx squared occurring twice. Because of this, we have the moment of inertia about y is causing this, and then we also tack on the point mass. It just happens to be that there's actually a duplicate point mass in here, just from equivalence, which I'll just simply write as 1/3 ml squared plus 2mx squared. Next up is the center of gravity. So the center of gravity occurs at x if it's sort of stable. Therefore, the periodic time is 2 pi root I over mgh. Just right up here is 2 pi square root of, now the moment of inertia again is 1/3 ml squared plus 2mx squared, divided by the mass of the whole thing, which is, we have 2mgx. Now, cancelling the m's and then multiplying top and bottom of here by 3, this becomes L squared plus 6x squared. And this becomes 6gx. So if we square this first to kind of get everything out, we can tack the 6g out of here, and we're left with L squared plus 6x squared all over x as t squared. And of course, taking the square root, we get this 2 pi squared divided by 3g, not equals, times L squared plus 6x squared all over x. Can always find t squared. That's the problem. I should have written that as t squared, because we're actually finding t squared, because we have to find the thing for part 2. So I'll rewrite that t squared is 2 pi squared over 3g times L squared plus 6x squared over x. Yep, same thing. So we need to find the point at which it's minimized. So we actually just take the derivative of t squared with respect to x. So this constant could just be plucked out. And on the inside, following the quotient rule, we have the bottom times by the derivative of the top. Take away the top times the derivative of the bottom, which is just 1, all over the bottom squared. And this is 0. Now, in order for something to be 0 in this, so if we have a divided by b is 0, this implies that a is 0. And so therefore, well, we have the x times the 12x, which becomes 12x cubed, minus 6x squared plus l squared, and that's 0. Oh, I'm not sure why I'm not writing that as x squared, sorry. There's definitely something wrong. That's the bottom times that, so this should actually be x squared. So then 6x, 6x squared. Oh, again, that's minus. Okay, I'm making just a few errors here. So that should be L squared. So minus L squared, so minus L squared is 0. So L squared is 6x squared. And so if we divide by the 6 and take the square root, we get that x is L divided by root 6 meters. And that's the value for L for which the oscillatory time is minimized.